Over the last couple of years, since I've been working with kites and photogrammetry, one of the things that's often overlooked are the actual sensors that we use, the cameras we use to collect imagery. And as I've tried to put up in the title, the better sensors we have, the better imagery we can collect, and the better output we can produce. So the key thing I want to get across during this talk is the selection of the camera we use and the mission planning are absolutely critical to the quality of the imagery we can collect. There's three things I want us to touch upon. Firstly, the exposure triangle for optimising the exposure of our imagery. Secondly, any noise that we generate in our imagery. And then finally, any image blur. And the scene up here was designed to show you what I see a lot of from my photography, a lot of poor imagery that you can acquire. So the very starting point then of our process is the camera we have. So to quote from the website called Clark Vision, the lens collects light, the focal length spreads out the light, and the pixel chops up the light into small details. The bigger the diameter of the lens, the more light we get. The longer the focal, the shorter the focal length, the longer the focal length, the less light per pixel we get as it spreads it out more. And the bigger the pixel, the more light per pixel we get. So, some very basics. We start off with a digital camera with a sensor, and that's recording light for us. Or rather, at a simpler level, it's counting photons that are coming onto our sensor. We then have the shutter speed, which controls the duration of our photon collection. So, how long do we let light onto our sensor for? Thirdly then, we have aperture, which is essentially controlling the diameter of our lens and so the volume of light that we're letting into our system. Not to forget also then ISO, which amplifies our signal. Now just to stress a point here, ISO doesn't change the sensitivity of your sensor. Your sensor has a fixed sensitivity. All it does is amplify the signal. Everything in your signal, including all of the noise as well. Okay, so the analogy that's often drawn in photography is with water. So the water here are our photons that are arriving at our sensor. The diameter of the pipe is equivalent to the aperture, so we can let more or less water through the pipe. The tap or the valve on our pipe here is equivalent to our shutter speed, so we can open the tap up for a certain amount of time and close it off. And then the size of the bucket here is the pixel size in our camera. The bigger the bucket, the more light we can collect. One further analogy you can draw here slightly is to think about putting a spray nozzle on the end of our pipe. If we do that and move the bucket closer to it, we're essentially changing the focal length of our camera, and that has the same effect. Okay, so in photography then, the exposure triangle is commonly used to think about exposing for a exposed photo, or creating a well-exposed photo, and we have this combination of aperture letting in more or less light, shutter speed letting in more or less light, and ISO changing the sensitivity, or changing the gain on, it says sensitivity here, but changing the gain on our sensor. So we need to let enough light into our camera, and those three things are the main controls we have for doing that. So what I want to think about now is what makes a good photo. We need high image quality if we're going to process it photogrammetrically. And there are 5 things I want to touch upon here. Firstly then, focus. We need our subject to be focused on the image plane of our camera, and that needs to be sharp. Typically what we would do with an SLR is to focus it at infinity, given the distance from our camera to our object. Secondly then, we have lens quality. The better the quality of the lens on your camera, the better it is able to perform in terms of letting in light, the amount of distortion in it, and the overall performance. Thirdly then, this is quite often forgotten, is diffraction. The narrower the aperture on your camera, the greater the amount of diffraction that you have, which blurs or reduces the contrast in your image. So this is just an example from a photography site going from an f4 aperture all the way up to f32, and you see a decrease in the sharpness of your image. Typically, for most SLR lenses, you will have the highest sharpness at often one stop back from the maximum aperture. So if you've got an f2.8 lens, then quite often the sharpest image will be acquired at around f4.5. Fourthly then, we have distortion, radial distortion, which has two components, pincushion or barrel distortion, which you need to account for in your processing chain. And then finally, we have noise in the digital system. There are a variety of different types of noise. Two I want to focus on now are perhaps the most important. Firstly, shot noise, which is the random variation in the arrival of photons at your sensor. That can be modelled using a Gaussian distribution. Now remember, these are integer data because we're counting individual photons, so you can model this with a Poisson process. Now if you do that, what it means is that the variance of our arrival of photons is parameterized as the square root of the mean. What that means in terms of your data is that as your signal increases, your noise increases at a slower rate. And that's really important in terms of thinking about the data you acquire. Secondly, you have read noise, which is related to the circuitry of the digital camera itself. That is fixed for every read, which means the lower the signal that you have coming in, or the darker your image, the higher the proportion of noise that read noise is. Okay, so in terms of mission planning, what takeaways can we get from this? Firstly, let's look at a couple of cameras. This is a professional level SLR, the Nikon D600. And the first thing you can see here is the size of the sensor, 35mm by 24mm. So we've got quite a large sensor in there, but it's also quite a high resolution camera at 24 megapixels, which gives you a pixel size of 5.9 microns. On this particular example, we would often fly a 24mm lens, which goes from f2.8, and this weighs a kilo, so it's not the lightest camera around. So you've got a nice example of settings for this particular camera. In contrast to that, this is the Ricoh GR, which has a 24 by 15mm sensor. At 16 megapixels, which gives you a pixel size of 4.8 microns. But this camera weighs 245 grams, so a fraction of the weight, and has a focal length of 18 millimeters. Now you'll see I've put up here effective focal length. Now that's because with these cameras you have what's called the crop factor. So here we have an example on the outside in the grey of a 35mm sensor, and you have examples of the size of the sensors made up from different types of cameras. Now as soon as you change the focal length and the size of the sensor, the effective focal length, or the field of view of the camera, changes. And you need to be aware of that when you're doing your mission planning, because it will vary for each and every camera you have. Effective focal length is used because pre-digital with film cameras, they were 35mm, so all lens at focal lengths people were familiar with were related to 35mm cameras. Okay, so camera selection. We want a wide field of view, and I normally fly somewhere around a 24mm field of view lens, because that gives a good view of the ground. The problem you get as soon as you go wide, shorter and shorter focal lengths is the distortion becomes bigger and bigger on the camera. If you fly longer focal lengths, then you have to move further away from the Earth in order to get a wider view of the ground, so it's a compromise between those. Weight is important. Do you fly a kilo camera or one that's 250 grams? And the resolution of the camera in terms of megapixels is very important. But there are some big takeaways here. Firstly, bigger pixels means more light, but less detail. You're going to have that trade-off in anything you do, more light versus less detail. So if you take more light in, you get a better signal-to-noise ratio, and you'll generally get a better dynamic range for the camera, which means better imagery, but you will get less detail. Okay, in terms of the camera settings then, always shoot in the RAW format for your camera. You'll collect 12 or 14-bit data for that, which means a much better dynamic range, as opposed to 8-bit data that you'd get with a JPEG. Shoot in a medium aperture, probably around f8. That will minimize any lens distortion that are at the edges of the lenses in terms of your radial distortion, but it should also minimize any lack of contrast from diffraction. You need a fast shutter speed, and I'd recommend anything over around 1/500th of a second. In order to balance the aperture and the shutter speed, you need to set the ISO into auto. You're far better off dramatically boosting the ISO up to maybe a 1600, 2000 or 3200 in order to maintain that shutter speed. Shutter speed is by far the most important thing to keep high. Finally, fix your focus at infinity, so your photos remain focused. One of the big things in the photography then to pull out is overexposed to the right. If you search this in terms of photography forums, you'll see that that is a key component. Now what this will do is it will overexpose your image, which you can later correct in post-processing. Make sure you do this without saturating any pixels, but what you're doing is boosting the signal-to-noise ratio here, so you'll get much less noise in your imagery. One final thing to note, motion blur. You get blur, you can calculate blur based upon this formula, which is the forward movement of your UAV in meters related to the size of your pixel in meters. Now, in terms of flight planning then, there's a couple of big things to take away. Firstly, better spatial resolution. If you want that, you need to decrease your flying height. Think about 121 metres. That's often the restriction for UAVs in terms of flying height, certainly is in the UK. So you need to be 121 or below. Size of your pixels. If you want better resolution, you need to decrease your pixel size, but remember, you're going to reduce your signal-to-noise ratio and your dynamic range, and you can increase your focal length. In terms of motion blur, you've got some competing effects here. Pixel size, flying height, focal length, shutter speed. Perhaps the simplest thing to change here is your flying speed. If you go slower, you're going to get less motion blur. So hopefully you've got a greater awareness of the impact of your camera